Hello. So in this video, we're going to be going into some details in data parallel operations. Now this is coming up later. I believe it's around week 6 or 7. So this is kind of a preview, but it should also help motivate you for studying and learning about these. These are some of the more fascinating things going on in computer science today. And honestly, the capabilities of the multi-core systems and the GPU systems, that's what's driving technology and driving technical innovation today. So as a background on the video, most of it's going to be a screen capture, so you're not going to see me. I've enlarged my screen quite a bit to make it easier to read, since screen captures are not always the best looking. And I'm going to be running a lot of Python code. Some of the code I'm going to be changing in real time as we're talking, and others, well, there will be some, some boring parts where you might have to wait a few seconds to see what's really going on and to understand the difference in computational speeds between just using the CPU and using the GPU, for example. I'm going to do some fun things. I'm going to crash the GPU, so at some point I'll be switching cameras because I can't keep doing the screen capture when the GPU is crashing. What else is going to be interesting? I'm using some advanced Python libraries that specifically support these parallel operations. One is called NumPy. NumPy, I'm going to be using that for parallel operations on the CPU and also multi-core operations on the CPU. I'll be able to demonstrate all of that and show it through the resource monitor built into Windows, which shows the activity in each individual logical core in the system. Other system that I'm going to use is called CuPy. It has CUDA built into it. CUDA is the graphics programming language created by NVIDIA. So when I'm using the CuPy, I will be running code in the GPU, and I'll be able to show you what is happening in the memory on it, and as well as its utilization. Same with the main system. Little about the system I'm using. It is not your normal desktop. It's a little souped up for the types of things I like to do. So it is pretty good at handling AI tasks, and it has an obscene amount of memory in it for doing things like this and whatever else comes along. So it's a Ryzen 5 5600X. I have 48 gigabytes of RAM. The graphics card is a GeForce RTX 2060 with 12 gigabytes of RAM. None of these are the latest and greatest, but these get the job done and will be more than worthwhile. Hey, Sancho! Sancho wants to say hi. Be more than worthwhile. I'm making an interesting video for you. So I'm going to cut over to the screen capture now. Let's talk about the difference between data parallel and task parallel operations. This is a topic that you'll need to understand well for the class. So a task parallel operation refers to doing separate tasks in parallel across either multiple systems, multiple cores, the multiple threads. Depending on how threads are managed, that could be one true thread per core, or it could be some other type of multi-threaded system, a multi-threaded programming environment, allowing you to, let's basically slice up a thread into multiple threads and let you do different things all at the same time. So task parallel, it's independent tasks. They don't rely upon each other. And they're different tasks. So like I said, this can be a system where different computers in the systems are doing different things, but all working together, maybe putting their outputs into a database or into a message queue, enabling the systems to interact with each other and to continue whatever job it is moving forward. Now, data parallel is what all of this video is going to be about. So you're going to be an expert on data parallel when this is done. So if data parallel, it means I'm doing the same task, but on different portions of the data. I'll still have my multiple threads and cores working on it. I can even have multiple computer systems working on it in data parallel environments using something called Apache Spark, for example, that can spread the same job across a cluster of systems. Now, in my data parallel environment, I've got a CPU with 6 cores and the equivalent of hyperthreading, so I have 12 logical cores. And that's going to be plenty. My cores are well provisioned because I've got 48 gigabytes of memory. So effectively each core can use, plenty of memory, several gigabytes per. Now, you've been staring at the task manager and the resource monitor for too long now, so let's get into the action. Now, I've already got a special command window up here, and this is a window for running CuPy operations. What this technically is a Python virtual environment created by a system called Conda. Python, for all the good it does, it's kind of a pain, and people have spent a lot of effort to solve some of those pain points, and one of them was the creation of Conda. Anaconda is the name of the project, I think, officially. So what a Conda environment is a complete running Python environment that you can custom configure independent of any other Python systems on your computer for specific types of jobs. So if you need to do something that uses some library in Python that conflicts with some other library, create 2 separate environments. Now the conflict's gone and you can still do your work. Now you still have to manage the environments that you have and all of that, but at least you can still do your work. I've got a few environments on my system right now. Some of these are for this demonstration. Some of these are for AI operations that I do. That's what LDM is for. That's for running stable diffusion libraries. But we're going to be just in CuPy for this. Now, there's a lot of the inner workings of computer systems that can be exposed by code. So we're going to take a look at some code here. Don't worry, this is not a Python class. I'm going to talk at a very high level. So the first thing we're going to do is I want to show you what some of the choke points, bottlenecks are in a CPU, and show you the difference between just running some operations and running operations that produce output as you go. I have 2 functions. One prints out intermediate results of the operations. One does not. They do exactly the same thing, and they're using NumPy for the operations. And we're going to run them. We're going to run these in a loop so that you can see how long they take and what the speed difference is. Because if I run it in too short a time, like if I just run them once, you won't gain any perspective on how long it takes. So here we go. So in the bottom window here, we're running, everything's done now. Now notice here, I'll highlight it. When it was being printed out, we had a duration of 5.74 seconds, basically. Without printing, same operations, took less than, what, 0.03 of a second. That's a dramatic change. That's a factor of 1, 2, well, 10, 100, like 200 times. I think that's about right. So, screen output takes a lot of time. Any type of log output is going to take a bit of time, and when you're writing code, you need to actually think about these things because it can distort your results if you're trying to figure out how fast something is, or if you're wondering how fast a logging system needs to be, etc., etc. So the actual math is fast, the output's slow. Back to why is that for a second? When I'm communicating with the screen, I'm sending data from the raw results of the CPU out through the GPU. So I'm traveling through the motherboard and sending streams of information from basically from one memory source to the other memory source on the GPU to create the images on the screen. There's a lot of activity going on that is cut out when you just do the operation. Now, I want to show you the real meat of these demonstrations now. We're going to get into operating with the GPU. So I switched to a new piece of code here. And in this case, I'm using CuPy. Now, the operations are going to be similar, but because I'm using CuPy, there's certain implications that happen. For example, in this method here called big array, I'm making an array of a given size. And because of using CuPy, it is automatically doing it on the GPU. I don't have to tell it to do it on the GPU. It's just going to do it on the GPU. Then I've got the similar matrix math functions here. They make arrays. And in this case, this one's making its array every time. But I've got another version that just makes the arrays once and then reuses the array. And that was really a test to see if creating a new array was a significant part of the operation. Turns out it was not. If you know about matrix operations, the dot product is a very heavy operation because it's basically multiplying everything by everything, if I'm recalling right. So down here in the main code, we're going to be running with the same array. So we take out array creation. We're going to take a look at how much memory was being used. And then at the end, we're going to allocate a big array. I call it the big boy. And we can calculate how much memory that would actually use. And we're going to do that actually in this discussion, because it's worth understanding, again, to be able to work within your limits, you need to be able to know how to calculate how much memory something's used. And that has to do, in some small part, honestly, with the CPU architecture and how numbers are being represented and what type of numbers being used, whether it's an integer or a 32-bit float or a 64-bit float. Those number of bits in use obviously dramatically change how much memory you're using, but also how much memory you're moving through the CPU. And that affects the speed of operations. Okay, because this is CuPy, I need to run in the CuPy window, which I seem to have lost somewhere. Nope, there it is. All right, so the function we're going to run with the Python code okay, it's CuPy parallels. Now, I've got a typo, I got to fix that. There we go. Python. Now we want to take a look at what's happening in the GPU during this. So we've got to get that ready. The GPU's doing some work right now. This steady 19%, that's because I'm recording the screen. Doesn't use a lot of memory, but it is using quite a bit of GPU. So now we're going to start running this. All right. GPU utilization, you see spiked up, and this was over really quick. So what happened? Okay, we just ran 3 iterations. They only took 1.5 seconds. The big array, this was 4 gigabytes of GPU memory. The general operation was using 1.7 gigabytes. Now, we didn't see a whole lot. We did see this spike. That was the, well, that's the CPU. Oh wait, no, sorry, no it's not. That was the GPU. Yeah, I'm on GPU. CPU during this process, maybe it did a little bit. Yeah, just a little bit, but nothing significant. So now we're going to run this same operation again, but using some different code and using a different technique. So I'm switching. This is kind of primitive, I know. I'm taking that code out, putting this other code in. So now we want to make sure we're doing about the same thing, right? So size 120, same array. We need to set the iterations. Okay, I was doing 3 iterations. So we're going to set this to 3. It's going to calculate the time of each one and then the total time. And then it's going to make a big array. And it's doing that in main memory, since this is not using the CuPy environment. All right. Let's keep this on top. Here we go. Now the CPU that's gone up. Well, let me just show you. Here's the CPU activity. Not doing a whole lot. Oh, it's already done. So that was anticlimactic. Let's change these up a bit. I want to do something a little more dramatic. Okay. Now, you know, I don't think I ran anything before. That would explain much. Okay, the first iteration, 14 seconds. We see the CPU is going as high as, it's spiked over 20, almost 25%. It's averaging around 17%, say. Memory, no real memory load because these are small arrays. We just did another iteration. So recall, when I was running these on the GPU, the total duration for 3 iterations was 1.5 seconds. Right now, we're looking at 14 seconds per iteration. And almost all of that time is spent in the dot product operation. Obviously, using the GPU to do this was a winner. Dramatic difference on matrix operations and performing the matrix operations, specifically in the GPU, in parallel. Now, are these running in parallel? I am using NumPy. We can explore that through the resource monitor. The resource monitor says, yes, we are running in parallel. Notice all these cores. Yeah, I'll get some scroll bars back. Multiple cores are loaded up during this processing. Not all of them. Some of them may be being, held for just regular system operations, right? Something is running, the graphics capture that's going on right now. Actually, we can see even more. So here's Python. Like it's running. You know what? I don't think that's the percent of CPU. That's not the number of CPUs. So this is still running because I set it for 30 iterations, but it is running in parallel on the CPU, and its performance time still got absolutely crushed when you run it on the GPU. That's really the lesson here. Given the opportunity to use the GPU, you should use the GPU. Now, we've got to, why am I still in the resource monitor? We've got to kill this operation. That's that guy. Okay. So, are there times when you may have to use the GPU instead of the CPU? There definitely are. As you noticed before, the GPU has 12 gigabytes of RAM, and the CPU has 48. Let's explore that a little bit. So I'm going to modify this code. This is the code that runs on the CPU. I'm just going to basically skipping all this. I really just want to see what happens right here. Now, the arrays that this is making are three-dimensional, and by default, this operation is using a 64-bit floating point value. So it uses 8 bytes. So we can calculate how big this is. So I don't think it's very big, but we're going to take a quick look. 170 times 170. It will seem like this is a big number, but I'll show you in a minute that it's really not. Times 8. So this is the number of bytes. So let's figure out how many megabytes. So we divide this by 1 million. 39 megabytes. I got to tell you, that's insignificant. Now, let's bring up a good number. I kind of know what the numbers should be since I've been working on this. We're going to go to an array that's 10 times larger in each dimension. But that means ultimately it's 10 times 10 times 10. So 1,000 times larger. Now we're talking. So I'm going to divide this by 1,000,000, put it into megabytes, and we still have 39,000 megabytes. That, my friend, if I divide by another 1,000, is the gigabytes of memory. I can do this on this system. So it's made for things like this. So we're going to allocate a big array, a really big array. And we're going to watch it grow. And there it goes. So this is the main memory. You're watching it being allocated right now in real time to just make one giant array. I'm not going to do any operations with it, just making it. Kind of shows you how long it takes to allocate it too. And that's tied to how fast is your memory and how fast is the motherboard connecting to that memory. So that moved all those numbers that were being generated, all of those 8-byte floats, pretty quickly. I mean, you know, it just kind of screamed up there pretty fast. You know, that must have been moving, well, I would say that was moving a few gigabytes a second. It seems about the right order of magnitude. Now, if I were to do this on the GPU would crash because it has 12 gig, and then I would no longer be recording. We can survive that crash. That's not a hard thing to do. If I use up all of my memory, though, on the CPU, that's a problem. The CPU it'll keep running, but you'll barely be able to move the mouse, and when it does move, everything will be delayed. You won't be able to change tabs, or if you do, it might take minutes to change a tab like that. Or you might try to open this up and it won't open. So if you do you know, exceed your main memory, you're going to have problems. The GPU is easy to recover. The operating system actually seems to reserve some memory so that you don't even lose your screen. I'll just lose my screen capture recording software, I believe. Okay, we are going to move into the next phase. So we did talk about the memory calculation. Let me just show you something. This is worth understanding. If I were to, and I've switched to the GPU environment. Now, say I do go for a big array in the GPU. Well, there we go, 800. Sure, why not? I think we've been doing that successfully already. So 800, we gotta calculate that, right? So what is that really? Okay, 800 times 800 times 800. And the default is still using 8 bytes. So you may have noticed this number. We saw this number before. This 4, well, so a close number. This is the total memory that was in use in the GPU at the time. So the baseline memory for running the system plus this extra 4 gigabytes of RAM, that's what we did to the GPU. So we're going to, let's go a little bigger. Let's go to 1,000. Go to 1,000 safely? Let's find out. Okay, 8 gig. Let's do it. There's our GPU, there's the GPU memory. Now this is going to go straight into it. It should go pretty quick. Oh, 8. It's captured in video. You saw it. It jumped up and it's gone. It was like 8.12. So, what did you see there? You saw that the GPU memory was allocated incredibly fast. I mean, the CPU and the main memory, that was moving data fast. But the GPU was much, much faster getting data or creating it. So what's going on there? Well, the GPU has its own memory. So there's no data transfer going on off of the GPU. The code was running in the GPU cores, and they are talking over a very wide data bus to the GPU memory, and nothing is leaving it other than, some information for the screen. So when you're doing it with the CPU, you're writing to the main memory from the CPU, and the bus is not as wide. If the bus is not as wide, it can't move data as quickly. What is a bus? Well, it's an electrical line. If you have an 8-bit computer with 8-bit memory addressing, you have 8 wires operating in parallel that go to memory, that literally go to pins on the CPU and then connect to pins on a memory chip. 16-bit, 64-bit, you get the story. 64-bit bus, ooh, so the width, 64 wires. It is a physical thing. So those wires are operating in parallel, 64. Now the bus on a GPU, I think my GPU, I'm going to say might be 192-bit bus, so significantly faster than the bus on the CPU, which is why you see the memory getting loaded quicker. I'm going to follow up with that demonstration of how long these operations take. So we're going to go back to 3 iterations. We don't care about this array. We're not looking at that. We're just going to look at how long does it take to do this math. Now we did these before, and the 3 operations were really fast. There you go. 1.37 seconds. Now, what are we going to do? We're going to look at the impact of changing the data type in the array. So, I've been saying the default was for 64-bit operations. So I've just changed the code here. So now we've switched to a 32-bit float, 4 bytes, half as much memory. So the arrays are going to be smaller, and for moving the data around while it's being computed on, you're now moving smaller amounts of data. So this is going to be faster. How much? Let's find out. Look at that. So roughly half the speed. And if you look at the memory numbers, these are the numbers here. This one's missing a whole 0. Just so I know it's hard to see. This is half of this. And this one here, which is my little array at the very end, is, that's twice the size of that, because in this run we were using 4 bytes to represent floats, so they had a lower precision. In this we were using 8 bytes. We were using what's called a double precision float. So very, very accurate number. So we've seen the operations are faster because they're using less memory. Not an unexpected result at all, but it's worth understanding those relationships and really asking yourself, Do I need double point precision, or can I just get by with float? Maybe you don't need floats. Maybe you can get by with integer. Maybe you don't need 4-byte integers. Maybe your range of numbers is smaller that you're operating with, and you can just put in 16-bit integers. And these are all various data types available in programming languages, and the CPUs know how to work with all of them, and the GPUs too. So you can control that amount of memory by changing the data types that you're using. We're moving on now to another way of operating with the GPU, and in general also multi-core operations on a CPU. Turns out that before you could have a multi-core system, the only way that you could manipulate every variable, every data point in an array was to loop through them and touch each one. That's what this code right here does. So this loop part here says for every element add 7 to it. So I go through every element in the array, each one, add 7, and I'm populating a new array as it goes. Now, because I'm using NumPy, this right here is making this parallel. So I am going to be using multiple cores. So it's not quite as primitive as, well, as it could be. I could do this without running in parallel. It would be really, really slow. Now that we have parallel operations available to us in a GPU, we can do not this looping technique, but add them all at once. So this plus symbol is not your normal addition. In this context, it has been overloaded because it's running in CuPy and it's using an array created in the GPU. When that is the case, and you use plus, what it's really doing is it's doing this operation on as many things in that vector as possible at the same time. Plus isn't the only thing you can do. There's a whole library of vectorized operations. So you can, anytime you're doing something with vectors, you can move it to the GPU. This is what's going on with AI, for example, machine learning. Doing vectorized operations or matrix operations in a GPU because it is really fast and efficient. But GPU memory costs more, and so sometimes you may just have to do it in a CPU loaded with a ridiculous amount of memory. But at least in the CPU, you can still utilize multiple cores and get some performance improvements out of it. Now, this code, there's going to be one difference here. This array here, first of all, these are one-dimensional arrays. This one has 10 million elements in it. On the GPU, I've decided to make it harder. So for the GPU, we're actually operating with 1 billion. So what's that, 100 times the size? And we're going to take a look at it, see what happens with GPU memory, and also take a look at what's going on in the multi-core operations as this is run. Okay, so those are my CPUs. Nothing is going on. GPU is just at that steady state because of my video recording. And now we're going to run this. Won't take long. GPU memory shot up. It's up to almost 12 right now. You see the CPU has got a little activity going on there, and everything's already done, but you can see all the CPUs went through some spiking. So what happened? time-wise. So doing the loop add, running all the cores, 2.75 seconds. But doing the vector add on an array that was 100 times the size in the GPU, doing all these parallel operations as well, was less than 1 second. You can see similar results in these next methods here, where we have, I did some dot product operations in NumPy and then ran them in the GPU. And you see doing the operation in the GPU was dramatically faster than all 12 cores on the CPU. What did those look like? Those were using some pretty big arrays here. But again, I can go to an array which uses 40 gigabytes of RAM, but I can't do that in the GPU. So there's some trade-offs. Now there's just one little extra thing that I'm gonna show you. I've switched environments. There's other libraries that can do things like just-in-time compilation. That's what numba does. Intel has a Python library that can do things faster, multi-core. What I found out in all of this was that CuPy is the way to go. It's the easiest to use. It works really well. Now what I just printed out was some information on my system. So it's kind of inspected the system here. So AMD, 12 CPUs, CPU features. All of these are instruction set architecture modifications to the base CPU. Like this AVX and AVX2, these are vector operations. These came out in the 90s. MMX came out in the 90s, multimedia extensions, and these let CPUs start working much faster, much more capable, internally doing vector operations with various size chunks of data. So they would be smart enough to, hey, I'm using a 64-bit bus overall, but I can divide that by 8 and move 8-bit numbers at once, 8 integers. Well, that's what you use for the color values on a pixel. You use 8-bit integers. So we started to get some real good multimedia capabilities. Then there's some security extensions here and a bunch of things I don't know what they are. Sort of knows my operating system. It's really Windows 11. Here's the CUDA information from the GPU. That's important stuff. I'm running pretty recent stuff. Maybe, it's probably the most recent. LLVM, this is a special compiler for converting Python into machine code directly and bypassing the Python interpreter. So numba uses LLVM to accomplish that. More information on my card, my GPU. It's found the location of all my various libraries. NumPy, this is important. NumPy supported SIMD. So this is for parallel operations. This is some of the code that I have installed. It's not finding everything, but it worked pretty well. Producing a report on what my system was like, kind of the whole system profile. So now that concludes these demonstrations. I'm not going to crash my GPU. I decided, well, sure, why not? Let's crash the GPU. What's it going to take to do that? Let's see. Parallels, big array. You can forget about that line. We're never going to get there. There, that's insane. We don't need to do any of those operations. Bring my window back. Now I'm going to switch my environment back. So anaconda, activate. There we go. We're going to be running parallels, and that's what's going to crash things hard. And all we need to do is see the basic task manager. All right, so there's the GPU. Now I'm going to start filming the screen of something else now, because I think my screen capture is going to crash when I run this. So here we go. Let's see what happens to the GPU. Well, the GPU actually protected itself. It would not even try to run that amount of space or use that much memory. Looks like I was trying to allocate millions gigabytes. Oh, it looks like 4 petabytes. A few too many zeros. Well, I hope you enjoyed this supplemental session on data parallel operations and how they can be achieved in Python working with either the GPU or the CPU. Now, as you notice, the GPU was dramatically faster, but has limitations. It can't use as much memory for at least the same price as CPUs do. So you'll still find massive servers with 2 terabytes or 10 terabytes or more of memory doing AI and machine learning type operations, since the GPU just doesn't have the memory to accomplish those. If you're interested in the code, I can send out the code for this if you want to run some Python yourself. If you've got a GPU and you want to try it out, just contact me through Canvas and I'll make that happen. Have a good day.